I've always been very curious about what is inside these large language models, LLMs. How do they actually work? And when I learned about DistilBERT, a smaller model that I can actually open up and peek inside using just a few lines of Python, I knew I had to try. In this video, I will take you along as we peek inside an LLM together. When I first heard that OpenWeights models were available to amateurs like me, I thought that might be a way in, right? A way to peek under these models. I've always been curious about them. So this video is not meant for experts. If you're already working deeply with LLMs, if you're fine tuning them, then this is probably, you may not learn anything from this video. But if you're a regular user and who's very curious, then I invite you to come along because I have been wanting to take a look to peek at what is inside these LLMs. BERT, a model that Google at that time was working on, had released, and people were talking about it. But I was not really using LLMs. I was not even aware of this space properly. Though I was kind of keeping an eye, and I knew and I had heard that it was really good for natural language processing NLP tasks. Turns out that BERT is one that over a period of time now, all of us have been using quite a bit, whether we know it or not, for question answering. It's apparently really, really good for NLP classification, sentiment analysis being one sort of classic use case, and also named entity recognition. I was sort of poking around Hugging Face when I came across this model. I was actually looking at small models when I found or started hearing about something called DistilBERT. So I got more curious, and when I looked into it, its definition itself was really interesting, right? A distilled version of BERT, smaller, faster, cheaper, lighter. So that got me really intrigued. I will show it to you live as well. But basically, I'm going to open my Colab notebook. And then the first thing that I will do, and I want you to do if you're following along, is to click on runtime. Then do you see here in the bottom where it says change runtime? Click on that. That will pull up this window, and mostly it will probably be CPU will be selected, and select the T4 GPU radio button and then hit save. Okay, that way it will switch to using a GPU. And then the next thing I'll do is I'll do pip install transformers, the transformers library. I'm going to install it in my Colab, and then I only have two sets of commands. So from this transformers, I'll import auto model, which is what we're going to use to load our model into memory. And I'll also be importing PyTorch. The model name, which I got from Hugging Face, is DistilBERT dash base dash uncased. Okay, so I'll just, it's only a string, and then I'm going to load that from the pre-trained, which is a method in auto model, and I'll give it the model name. Once I hit run, here it will take some time because it will have to load it into the notebook or into Colab's memory. And then once it's done, you should see these things. If you see model.save tensors 100%, then it's done, and the entire model is in your Colab's memory. Okay, let's try this out. I've just opened an empty Colab notebook, and the first thing we have to do is to go to runtime, change the runtime type. You see here, for you it should be CPU because I just tested this out. It's already T4 GPU. Then hit save. And if you look over out here, you should see that it is actually indeed connected to T4. And then the first thing that we would do is to install the transformers library. Okay, so let's get that going. And while it's doing, I will also get my couple of other libraries which I know I would need. So the reason I'm getting transformers is that I want auto model, and I also want to import PyTorch. So let me run that as well. Okay, everything is imported now. The next thing, only these two lines. And I'm just giving a model that I want to examine. Okay, that is done. As you can see that a big JSON as well as the models tensors, right? They've been loaded into memory. Then I have this command I've already typed. So a model has a tuple called named parameters. All this I had to look up. And I'm just taking each one of them and printing them layer by layer, each layer's name and its size. So let's run this and see what happens. There it is. So now we're actually able to look, we are peeking inside DistilBERT. Once I had the model loaded in my Colab notebook, I realized that I didn't know where to start. What does it even mean to look inside an LLM, inside a model? What should I actually be checking for? But one thing that has always puzzled me is all these big numbers that I hear about model names, right? 3 billion parameters, 7 billion parameters, 20 billion, 70 billion parameters. Why so many? And what are all these parameters doing? So I decided to start small. I picked the smallest reasonable LLM I could find, DistilBERT. And my first test was just to verify if the number of weights that I am able to look at, does it even match what the model's name is, what the documentation says. I wanted to see for myself if, as advertised, DistilBERT does indeed have 66 million parameters. So let me show you the commands I used, right? First, I went layer by layer, and there is a method for each parameter called parameter.size, and I printed that out. But what it gives me is that it gives me the dimensions of each tensor, of each PyTorch tensor, right? So it's m by n, how many columns, how many rows. But what I really need is the total elements. It turns out that there is also a method called param.numElement, Numel. And when I printed this, see here, there's 23 million right in the first layer, embeddings, and then there is 400,000 and so on. So now it's just a matter of how would I go about totaling all of these. So I wrote this code, very simple. I just said, hey, I'm going to keep a running total. And for each layer, I will just add it to, I'll calculate I'll pick the number of elements and add it and print it. And since it's such a large number, I'm going to divide it by millions. And here it was indeed 66.3 or 66 million. So the first thing, I was very happy that I was indeed able to see. We just have to now total up all of these to get the total parameters. So I'm keeping a running total, and then I'm just going to add it up to get a number. And that's a big number. So let me just see in millions. So 66 million parameters. That's what DistilBERT has. Again, I had read that DistilBERT, unlike BERT, which has apparently 12 transformer layers, DistilBERT has half as many, 6. And I wanted to see that for myself. So I ran this small piece of code, and indeed, and there are 6, and I even printed them out. I'll just show you here. So it turns out that each transformer layer set, if you will, is made up of 16 thinner slices, right? Each slice here is a tensor in itself, starting from attention and then the SA layer and feed forward network and all of those things. 16 of these for layer 0, and then I also printed the last one. So there are indeed 6 layers. Okay, so I was happy that I'm able to see that and verify for myself. I wanted to look at the numbers themselves, at the weights, and see how they were distributed. For a given layer, for any layer, I wanted to see the minimum, maximum value, basically the range, And I'm very curious to see if I plot them, what will that look like? That histogram look like? Will it lead to any insights? And finally, I'm also curious to know if most of these weights are very close to zero. In the sense, are these layers of weights and biases, are they very sparse? That's what I'm going to look at now. Then the question is, what are the numerical values, right? So you can actually go to any one of these, just use model parameters, and then you can index it, go to a particular tensor and print it out. I was curious about the distribution, so I just printed its max and min. So in this case, the max value is 0.6, but the the least value or smallest in that particular tensor that I was looking at happens to be minus 1.1, around that. So it came back with this. It took about a minute. Maybe I could have made the code more efficient, but anyway, for our purposes, you can see that most of the values, the bulk of this distribution seems to fall between minus 0.2 or minus 0.15 and plus 0.1 or so. So it's all, the mean is below zero. We could run all of that, and I'm not sure if that's insightful or not, but for me at least it gives me a feel for what is inside each one of these layers. Always curious about is to see how close to zero are these. So after I played around with this tolerance, you can read this code at leisure, but the bottom three lines here are the most interesting, at least to me. It turns out that 97, right? 97 and a half, and in this case, literally 99.5% of the tensor's values are within a tolerance of 0.1. So which means that they are between minus 0.1 and plus 0.1. Almost everything is basically a very sparse matrix. Only around 2 or 2.5% of the values are even beyond that. So again, I don't know what all of these, what insights I can draw, but at least I get a sense for the distribution. One final thing I have been very curious about, okay, if you're building 6 different layers, how different are they? So I picked this one at random called an attention layer, which has a Q like QKV. I picked the linear weights of the Q tensor for the very first transformer and the sixth transformer, so 0 and 5. When I compare them, you can see here that they are definitely different, but they're not that different. Okay, so this is 10 raised to minus 5, and this is 0.0002. So, okay. And then the standard deviation is quite comparable. And then the min and the max here are minus 0.7 to 0.49. In this case, they happen to be very close to one another, 0.6 to plus 0.6. Okay. So we did verify that there are indeed 66 million parameters. Okay. So when I totaled all the parameters up for DistilBERT, as the name as advertised, there were 66 million parameters. So I was happy to see that. And indeed, when we look closely, there are these beyond the 3 or 4 embeddings initially to get it set up. There are 6 sets of layers, what they call the transformer layers, numbered from 0 through 5. So yes, and they are stacked. They're exactly the same over and over again. So in a nutshell, this whole model, this LLM and perhaps all the other LLMs are nothing but giant sets of layers and layers of numbers. They're tiny. Typically, when I looked at many layers and they all seem to be between -1 and +1. The mean seems to be very close to zero, but not exactly zero, negative numbers. But that's what I could find. But here is the interesting part. When a token, or rather repeatedly when tokens are passed through these sets of layers, it seems to lead to the emergence of properties that seem magical, right? That seem to derive meaning simply by running these tokens through these numbers and it pointing to different output. So my conclusion is the magic of LLM is that there is no magic. Okay, somehow these numbers they work. Today we only scratch the surface. I wanted to see for myself what the various layers of an LLM looked like and the numerical values of the weights and biases. But that's really just the surface. There is so much more that we could look into in terms of attention layers, transformers, embeddings, but those will have to be future videos.